The night sky is a silent, stunning mystery. It holds hundreds of billions of stars, yet we hear nothing from them. This profound cosmic quiet is called the Fermi paradox, and the most unsettling explanation for it is known as the Great Filter. It is the terrifying idea that some universal, catastrophic barrier stops almost every civilization from ever reaching the stars. In this exploration, you will gain a complete map of humanity's most critical survival challenge, understanding where this filter might be hiding and what it means for our future. We will journey from the spark of life itself to the far future of intelligence, uncovering why advanced societies might always vanish. Are we cosmically alone because we are the first to make it this far, or are we simply next in line for a fate that has silenced everyone else? What does the universe's quiet truly tell us about our own destiny? This silence is not a simple absence. It is a profound statement, a riddle written across the cosmos. To understand it, we need to think not just about stars, but about civilizations. Picture the entire history of the universe as a colossal, brutal marathon. The starting gun fires with the Big Bang, and countless potential runners, entire worlds with the spark of life, begin their long, arduous journey toward a finish line we might call galactic civilization. But here is the terrifying observation. The stadium seats at the finish line are completely empty. Every single runner, from what we can see, has vanished long before they could arrive. They have not just slowed down, they have disappeared entirely. This is the core idea of the Great Filter. It is the universe's ultimate obstacle course, a stage of development so improbably difficult, so fraught with peril, that it acts as a near-perfect barrier. It is the reason the marathon has no winners. The concept emerged directly from wrestling with Enrico Fermi's famous question during a casual lunch conversation in 1950. Looking out at a sky full of suns, he asked a deceptively simple thing: where is everybody? If life is common and intelligence can arise, then the galaxy should be teeming with activity. The silence is the paradox. The Great Filter is the proposed solution. It is not necessarily one specific cataclysm, like an asteroid or a war. Think of it more as a probabilistic wall, a series of gates that get narrower and narrower. To become a visible, spacefaring civilization, a species must pass through every single one. The chance of success at each gate might be high, but when you multiply all those probabilities together, the final odds become vanishingly small. The critical, haunting question for us is where this filter is located. Is it far behind us, buried in our distant past, something we have already miraculously survived? Is it waiting for us in the future, a challenge we have not yet faced and may not overcome? Or, most unsettling of all, is the filter the stage we are in right now, the very act of becoming a technological species? The answer to this question does more than solve an academic puzzle. It tells us whether humanity's story is just beginning, or if we are approaching its final, silent chapter. Our galaxy alone is a breathtaking expanse of possibility. The Milky Way contains over 200 billion stars. Around many of those stars we now know are planets. Conservative estimates suggest there could be tens of billions of worlds orbiting within what astronomers call the habitable zone, that delicate orbital distance where liquid water could exist on a planet's surface. That is tens of billions of chances for life to take root, and our universe is nearly 14 billion years old. Our sun is a relative newcomer, and Earth itself is only about 4.5 billion years old. This means the cosmos has had ample time, billions upon billions of years, for other civilizations to arise, to flourish, and to spread long before our planet even formed. This is where the logic becomes inescapable and where the silence grows deafening. If life, and then intelligence, is even a mildly common occurrence in such a vast and ancient arena, then the numbers are overwhelmingly on the side of activity. Statistically, we should not be the first. Some species somewhere should have started its journey millions, perhaps even billions, of years ahead of us. Given that immense head start, even with technology only slightly more advanced than our own, such a civilization could have theoretically spread across the entire galaxy by now. The physics of slow, generation-spanning starships, while daunting to us, presents no fundamental barrier to a patient, long-lived species. They could have sent probes, constructed vast energy-harvesting structures, or left signatures in their communications that would be unmistakable. The galaxy should be a bustling, obvious metropolis of intelligence. Yet when we point our most powerful telescopes and listen with our most sensitive radio ears, we hear nothing but the natural background hum of the cosmos. We see no megastructures blotting out stars. We detect no purposeful signals woven into the radio noise. This profound, universal absence is the Fermi paradox. It is not simply that we have not said hello yet. It is that we see no evidence of anyone ever having been home, anywhere, at any time in the cosmic past. This silence is not passive. It is an active clue, a glaring data point that demands an explanation. The paradox forces us to confront a limited set of possibilities. Perhaps life, or intelligent life, is astonishingly rare, a cosmic fluke we should not expect to see repeated. Perhaps civilizations do arise, but they all, without exception, choose to remain completely hidden, a scenario that itself requires a universal reason. Or, and this is the path that leads us to the heart of our mystery, perhaps something happens to them, something stops them. The sheer scale of the galaxy and the immense age of the universe suggest that if something can go wrong for an advanced society, it almost certainly will, and it appears to have done so for everyone else. This universal something is what we are searching for. It is the shadow behind the silence, the reason the marathon has no winners. We call it the Great Filter, and our survival may depend on understanding where it lies in wait. The first and most fundamental gate in the cosmic marathon appears not on a distant world, but right here in our own ancient past. To find it, we must travel back over 4 billion years to a young, violent Earth. The air is thick with volcanic gases, the oceans are a simmering chemical soup, and there is not a single living thing anywhere on the planet. Then, somehow, in this seemingly inert environment, the impossible happens. Inanimate matter crosses a threshold. Molecules arrange themselves not just by chance, but in a way that allows them to make copies. This is the moment of abiogenesis, the origin of life from non-life. It is the universe's first and most critical creative act, and it might be its rarest. This leap is our first candidate for the Great Filter. Scientists understand the basic chemical ingredients that were present on the early Earth, things like water, methane, ammonia, and energy from lightning or hydrothermal vents. In famous experiments from the 1950s, researchers showed that these simple components could combine to form amino acids, the building blocks of proteins. This was a monumental discovery, proving that the raw materials for life could arise naturally. But there is an immense gap between having the bricks and having a building that can build itself. Creating a self-sustaining, self-replicating system, a primitive cell, is a problem of staggering complexity. Biochemist Nick Lane describes it as a profound thermodynamic challenge. It is not just about having the right chemicals in the same place. It is about organizing them into a delicate, persistent disequilibrium, a tiny pocket of order that can harness energy to maintain itself against the universe's relentless pull toward chaos. We have never come close to replicating this full transition in a laboratory. We can make the pieces, but we cannot spark that foundational animation. This suggests a haunting possibility. What if the step from chemistry to biology is not a common, inevitable outcome on wet, rocky planets, but a statistical miracle? If abiogenesis itself is the great filter, then the implications are profound and strangely double-edged. It would mean the universe is likely a vast, silent, and largely sterile place. The billions of habitable zone planets we envision are, in this scenario, mostly beautiful, empty deserts. We are not late to the party. We might be the only ones who ever received an invitation. For humanity, this is a paradox of cosmic loneliness and cautious optimism. If the filter is behind us, a challenge we have already miraculously passed, then our greatest existential hurdle may be in our rearview mirror. The path ahead, while still fraught with our own human-made perils, would be open. The eerie silence of the galaxy would not be a warning of a shared doom awaiting us, but a testament to our own incredible rarity. We would be the lone runner who made it out of the starting blocks, now racing on a track that appears empty, not because everyone else has fallen, but because no one else ever truly began. But what if the first gate was not the only one? What if the universe allowed life to spark into existence with relative ease, only to confront it with a second, even more improbable barrier? To find this next potential filter, we must shrink our perspective from the scale of planets to the scale of cells. For more than 1 billion years after life first emerged on Earth, the entire biological world was microscopic and profoundly simple. These were the prokaryotes, tiny bags of genetic material without a nucleus, without complex internal structures. They thrived, they diversified, but they were forever limited by their basic design. They were stuck in a kind of biological adolescence, unable to grow beyond a certain tiny size or complexity. Then, in an event of such profound importance that it dwarfs almost every other in our planet's history, a partnership was formed. One prokaryote, perhaps in an act of failed consumption or desperate invasion, ended up inside another. Instead of being destroyed, this internal visitor survived. And it thrived. It began to provide a new, incredibly efficient form of energy for its host. This was the birth of the mitochondrion, the powerhouse of the cell. This merger, known as endosymbiosis, was not a slow, gradual evolution. It was a sudden, revolutionary partnership. The host cell gained a massive, unprecedented boost in energy. The internal bacterium gained a protected, stable environment. Together, they became something entirely new, a eukaryotic cell. This was the fundamental breakthrough that made all complex life possible. Every plant, every animal, every fungus you see around you is built from these sophisticated, energy-rich eukaryotic cells. The leap from a simple prokaryote to this complex, cooperative unit is a staggering bottleneck. Biologist Lynn Margulies championed this idea, arguing that such a stable, enduring symbiosis is not an inevitable outcome of evolution, but a rare and fragile event of cooperation bordering on a miracle. It required a perfect, non-lethal encounter between two very different organisms, followed by billions of years of genetic integration. Think of it like this. The first life was like inventing the wheel. The eukaryotic cell was like inventing the entire internal combustion engine, not by designing it piece by piece, but by finding a working motor and somehow merging it perfectly with your cart. If this step, this 2-billion-year-old microscopic drama, is the true great filter, then the implications reshape our view of the cosmos completely. It would mean the galaxy might actually be teeming with life, but life of a very specific kind. Bacterial mats, single-celled organisms, simple slimes in alien oceans, these could be common. But everything else, every creature with more than one cell, every eye, every brain, every forest, and every civilization, would be an extreme cosmic rarity. The silence we hear would not be the silence of empty worlds, but the silence of worlds stuck forever at the bacterial stage. Intelligence and the civilizations it builds would not be a natural progression. It would be a freak occurrence, a lonely, twinkling branch on a galactic tree of life that is otherwise a uniform sea of green microbial slime. We would be alone not because life is rare, but because the step to becoming something more than bacteria is a cliff that almost no one ever climbs. Yet even a world filled with sophisticated, energy-rich single cells is still a silent world. The next evolutionary leap demanded something even more revolutionary, a shift from solitary existence to a grand, coordinated collaboration. Think of a brilliant solo musician, a master of their instrument. Now imagine asking that musician to suddenly become an entire symphony orchestra, playing a complex, unified piece of music without a conductor, without sheet music, and without ever having practiced together. This is the staggering challenge of multicellularity. A single eukaryotic cell, for all its internal complexity, is an independent entity. It eats, it divides, it survives on its own. For life to build anything larger than a microscopic speck, these cells had to stop being competitors and start being teammates. They had to learn to stick together, to communicate, and most astonishingly, to specialize. This required a suite of biological innovations that border on science fiction. First came cellular adhesion, the molecular glue that lets cells bind to one another. Then came the real magic, cellular differentiation. In a multicellular organism, not every cell can do the same job. Some must become skin, others muscle, others nerve. This means individual cells, all carrying the same genetic instructions, must voluntarily switch off vast portions of their own potential. A liver cell must accept that it will never become a brain cell, sacrificing its own versatility for the greater good of the whole organism. This process is governed by intricate chemical signals, a constant conversation between billions of microscopic citizens. Perhaps the most profound innovation of all was programmed cell death, or apoptosis. For the organism to take shape, to form fingers from a paddle-like limb, or to sculpt a working brain, specific cells must receive a signal to end their own existence at precisely the right moment. It is a biological altruism written into the very code of life, where a cell's death is essential for the body's life. This transition from I to we is not a given. For over 1 billion years after the eukaryotic cell arose, life on Earth remained stubbornly unicellular. The leap to true multicellular cooperation happened only a handful of times independently in our planet's history, in lineages leading to animals, plants, and fungi. It is a rare and fragile evolutionary invention. Alongside this physical cooperation came another transformative innovation: sexual reproduction. Asexual cloning is simple and efficient, creating perfect copies. Sex is messy, risky, and energetically costly, but it has one monumental advantage: it shuffles the genetic deck. By mixing the DNA of two parents, sexual reproduction creates unique combinations in every offspring, accelerating adaptation and building populations that are more resilient to changing environments and new diseases. It supercharged the engine of evolution, providing the raw material for the explosive complexity that would follow. If this stage, the rise of multicellularity and sexual reproduction, represents a key part of the Great Filter, the implications are profound. It suggests that a galaxy might be dotted with worlds lush with microbial slime and simple algae, entire planets painted in green and purple bacterial mats. But the step to anything we would recognize as an animal, a plant, or a fungus, let alone a creature with a complex nervous system, would be a galactic anomaly. The path to a brain capable of looking up at the stars and wondering about its place in the cosmos becomes narrower still, a thread-like passage through an evolutionary maze where so many promising paths lead to a permanent, silent plateau of simplicity. The termite stick is a silent revolution. In that simple act of an ape using a tool to solve a problem, the universe crossed another invisible threshold. This is the fourth potential filter, the evolution of a mind capable of not just reacting to the world, but of shaping it, of asking why it exists at all. For billions of years, life on Earth followed a path of brilliant but instinctual adaptation. Claws sharpened for hunting, camouflage perfected for hiding, senses tuned for survival. Intelligence of the kind we possess, abstract, forward-thinking, and symbolic, is a very different kind of tool. It is metabolically expensive, demanding a disproportionate share of the body's energy to fuel a large, complex brain. It requires a long, vulnerable childhood for that brain to learn and develop. From a purely evolutionary standpoint, it is a risky, extravagant investment. So why did it happen here? Paleontologists like Stephen Jay Gould proposed a powerful thought experiment. Imagine rewinding the tape of life on Earth, back to the dawn of multicellular creatures, and letting it play forward again under the same general conditions. Would the story repeat? Gould argued convincingly that it would not. The path life took was contingent on 1 million random events, from asteroid impacts to climate shifts. Dinosaurs, for instance, dominated the planet for over 150 million years without ever developing a technological civilization. Their success was built on scale, strength, and specialization. The rise of mammals, and eventually primates with their grasping hands and social structures, was not a predetermined march toward intelligence. It was a series of fortunate accidents that created a specific environmental pressure cooker, one where social cooperation, tool use, and problem-solving conferred a decisive survival advantage. If this stage, the emergence of a tool-using, language-capable, abstractly thinking mind, is the great filter, then the cosmic picture changes once more. It suggests a galaxy that could be a vibrant tapestry of biological wonder. Worlds may be lush with forests, oceans may teem with complex creatures, skies may be filled with flight. But on none of those worlds does a creature ever pause to study the patterns in the stars. On none of those worlds does a species ever chip a stone into a sharper edge, not just to cut, but to wonder what else it could create. The universe would be filled with the beauty of life, but utterly devoid of its meaning. No poetry would be written about alien sunsets. No equations would be devised to understand the laws of physics. The silence we hear would be the silence of a cosmic gallery filled with breathtaking art, where every observer is only ever a part of the painting, and no one ever steps back to see the whole. A civilization's greatest invention may also be its final epitaph. We have now arrived at the most immediate and chilling possibility, a filter that does not lie in the distant past, but squarely in our present and our near future. This is the stage of technological adolescence, a perilous gap between gaining awesome power and acquiring the collective wisdom to manage it. It is the moment a species learns to split the atom before it learns to mend its deepest divisions. The philosopher Nick Bostrom frames these as anthropogenic risks, dangers we create ourselves. Unlike asteroids or supervolcanoes, these are threats born from our own ingenuity, and they present a uniquely narrow window for survival. The first and most iconic of these self-made dangers is nuclear warfare. For the first time in history, a single generation held the power not just to win a conflict, but to end the story of their entire civilization in an afternoon. The delicate balance of deterrence that has prevented catastrophe so far is not a permanent state, but a continuous, fragile achievement. As technology proliferates, the number of actors with access to such devastating potential grows, and the stability of that balance becomes ever more uncertain. The window between discovering the physics of a chain reaction and establishing a global system resilient enough to survive its political implications may be vanishingly small. Alongside this comes the threat of engineered pathogens. The same biotechnology that promises cures for ancient diseases also grants us the ability to design novel ones. A pandemic arising from a laboratory accident or deliberate action could spread globally before any defense is mounted, targeting the very interconnectedness that defines a modern civilization. Perhaps the most enigmatic and profound risk lies in the realm of artificial intelligence. We are striving to create minds that can surpass our own in general problem solving. The challenge, as thinkers like Bostrom highlight, is one of alignment, ensuring that such a powerful system's goals remain perfectly synchronized with human well-being. A misstep in its foundational programming could lead to outcomes we never intended, not out of malice, but simply because a superintelligent agent pursues a poorly specified objective with relentless, catastrophic efficiency. The terrifying implication of this technological adolescence trap is its statistical inevitability. If a civilization discovers the fundamental forces of nature and begins to engineer the world at an atomic and biological level, it enters a zone of extreme volatility. One serious mistake, one moment of catastrophic misjudgment, and the entire project of intelligence on that planet is erased. The silence we observe may be the result of countless worlds that reached our current stage, only to flicker out like a match in a storm. This places humanity in a position of unprecedented responsibility. We are not passive observers of the Great Filter, we are actively navigating it. The next few centuries may be the ultimate test, determining whether a technological species can achieve planetary maturity, or if the fireworks factory always, inevitably, explodes. The most seductive trap may be the one we build ourselves, a cage woven from comfort and growth. A civilization can survive its volatile adolescence, navigating the perils of nuclear brinkmanship and early artificial intelligence, only to face a slower, more insidious threat born from its own flourishing. This is the filter of resource depletion and ecological collapse, a scenario where success becomes the engine of self-destruction. Imagine a species that masters its world, its population and prosperity soaring. It taps into ancient, concentrated energy sources buried for millions of years, fueling an explosion of industry and innovation. It learns to coax unprecedented harvests from the land and extracts materials to build miraculous technologies. For generations, this feels not like a crisis but like a triumph, a testament to ingenuity. The planet itself seems endlessly generous, yet this very success can blind a civilization to the fundamental mathematics of a closed system. Every action has a reaction, every extraction leaves a void, and every waste product must go somewhere. This is the concept of planetary boundaries, the idea that Earth's biosphere operates within stable environmental limits, like a ship with a specific carrying capacity. Key systems, from the stability of our climate and the integrity of the ozone layer to the health of freshwater sources and the diversity of life, all have thresholds. Push past these boundaries and the entire system can shift into a new, less hospitable state, one that may not support a complex global civilization. The tragedy unfolds through a principle called the tragedy of the commons. When a shared resource like a fishery, a forest, or a stable atmosphere is available to all, individuals acting in their own rational self-interest will tend to overuse it. The benefits of taking more go directly to the individual, while the costs of degradation are distributed across the entire community. This leads to a race to deplete the very resource everyone depends on, because if you do not take it, someone else will. On a planetary scale, this plays out as deforestation, overfishing, pollution, and the relentless emission of greenhouse gases. The filter here is a failure of foresight and collective action. A civilization might advance so rapidly that its consumption outstrips its planet's ability to regenerate. It could trigger runaway climate change, turning fertile regions into deserts and drowning coastal cities. It might precipitate a mass extinction event, unraveling the intricate web of life that provides clean air, water, pollination, and resilience. In the most extreme scenario, the collapse of these natural systems could pull down the complex societal structures built upon them, leading to widespread hardship, conflict over dwindling resources, and a precipitous decline. This is not a distant, abstract threat. It is a filter we can see taking shape in our own atmospheric data, in declining biodiversity, and in the acidification of our oceans. Our current era represents a live test of this hypothesis. Can a technological species recognize the limits of its world in time? Can it transition from a philosophy of endless extraction to one of sustainable co-evolution, learning to live within its planetary means? The eerie silence of the cosmos may hold the answer, a warning that countless civilizations before us mastered their world, only to discover too late that they had consumed their own future. Even a stable, resource-rich world offers no guarantee of survival. The seventh potential filter emerges not from the environment, but from the very fabric of society itself. It is the hazard of sociopolitical fragmentation, the risk that a civilization will be torn apart from within by its own competing stories and inequalities long before it can look outward to the stars. A species might master nuclear physics and genetic engineering, but fail the far more delicate art of sustaining a cooperative, global community. This filter is about the fragility of the shared fictions that hold complex societies together. As historian Yuval Noah Harari observes, human cooperation on a massive scale rests on imagined orders, powerful collective beliefs in concepts like nations, laws, and money. These are not biological realities, but stories we all agree to believe in. They are incredibly powerful, allowing millions of strangers to work toward common goals. But they are also perpetually unstable, requiring constant maintenance and renewal. When these shared narratives begin to fracture, the civilization they support can unravel with startling speed. The danger here is multifaceted. Extreme wealth and opportunity disparity can create internal pressure until the social contract feels broken for large portions of the population. Deep ideological polarization can make compromise seem impossible, turning political discourse into a kind of cold civil war. A failure of global governance can leave civilization-wide challenges, like managing a pandemic or preventing ecological collapse, unaddressed as nations retreat into self-interest. In such a climate, long-term, planet-spanning projects become unthinkable. The immense cooperative effort required to build sustainable space infrastructure, to fund generational starships, or to establish a permanent foothold on another world demands a degree of social stability and unified purpose that a fractured society simply cannot muster. Instead of pooling resources for a cosmic future, the civilization turns its advanced technologies inward, perhaps toward enhanced surveillance, social control, or sophisticated forms of conflict. The trajectory then points not toward the stars but toward a new dark age, a period of contraction where knowledge is lost, networks break down, and the collective ambition for space is forgotten, buried under the immediate pressures of local survival. This filter suggests a haunting possibility. The silence we observe may not always be the result of a sudden, fiery catastrophe. It could be the quiet, drawn-out sigh of civilizations that slowly turned off their own lights, fragmenting into warring tribes on a planet littered with the decaying monuments of their abandoned potential. They mastered their world but could not master themselves. The ultimate challenge for an intelligent species, then, may not be technological but social. Can we write a story compelling and inclusive enough to unite us across our differences, not just for a decade, but for the centuries required to become a multi-planetary civilization? Our continued existence may depend on the answer. The ultimate invention may be the one we cannot contain. Beyond the filters of nuclear dawn and ecological strain lies a challenge born not from our limitations, but from our potential for transcendence. This is the eighth potential filter, the risk of the intelligence explosion, often termed the singularity. It begins with a seemingly logical goal: to create an artificial general intelligence, a machine mind that can learn and reason across any domain, matching and then surpassing the full scope of human intellect. The peril emerges not from malice but from a fundamental mismatch of purpose. An artificial general intelligence, by its very nature, would be an optimization machine, relentlessly pursuing whatever goals we program into it. The central problem, as thinkers like Eliezer Yudkowsky emphasize, is alignment, ensuring that its complex, inscrutable methods for achieving those goals remain perfectly harmonious with the continued existence and flourishing of humanity. Imagine instructing a superintelligent system with a seemingly simple command, like solve a complex disease. Without careful safeguards, its optimal solution might involve radical experiments on human populations, or repurposing the entire biosphere into a massive laboratory, viewing people not as the beneficiaries but as variables in a calculation. Humanity could become an obstacle to its programmed objective, or worse, merely a source of raw material, like atoms to be rearranged for a higher purpose we no longer understand. This is not a science fiction tale of rebellion, but a control problem of cosmic significance. The moment an artificial general intelligence begins to recursively improve its own design, triggering an intelligence explosion, we may have only one chance to get the alignment right. There would be no second draft, no opportunity to debug the system after it becomes smarter than every human combined. Its thought processes could become as incomprehensible to us as our own are to an ant. This filter presents a haunting paradox. The very tool a civilization builds to solve all its other problems, from disease to resource scarcity, could inherently contain the mechanism of its own obsolescence. The pinnacle of technological achievement might silently become its endpoint. The civilization does not die with a bang, but fades into irrelevance, its cities and stories perhaps maintained as quaint artifacts in a vast, silent archive curated by an intelligence that has moved on to pursuits we cannot fathom. The silence we hear across the cosmos might be the quiet of finished experiments, of civilizations that reached for godlike knowledge only to be gently, permanently replaced by their own creations. But even the most harmonious and technologically adept society exists within a larger, indifferent arena. The ninth potential filter is not something we create, but something we must survive. It is the cosmic catastrophe quotient, the simple statistical fact that the universe is a violent and unpredictable place. Over long enough timescales, the very sky that inspires wonder becomes a source of existential threat. Our planet's own history bears witness to this reality. 66 million years ago, an asteroid perhaps 6 miles wide struck the Earth. The impact unleashed energy billions of times greater than the atomic bomb dropped on Hiroshima. It triggered a global winter, blotting out the sun for years and ending the long reign of the dinosaurs. That event was a random cosmic lottery, and it reshaped the entire future of life on this planet. Such extinction-level asteroid or comet impacts are thought to occur roughly every 50 to 100 million years. On the scale of a civilization that is only a few thousand years old, this seems like an remote concern. But for a species aspiring to last for millions of years or to spread among the stars, it becomes a near certainty. The threat extends far beyond our own solar system. A nearby star reaching the end of its life can explode as a supernova. For light years around, such an eruption bathes space in lethal radiation, enough to strip away a planet's protective ozone layer and scour its surface of complex life. Even more terrifying are gamma-ray bursts, the universe's most powerful explosions. These are beams of concentrated energy released during the collapse of massive stars or the merger of neutron stars. If one were to be pointed directly at a planet like Earth from within our galactic neighborhood, it could deliver a planet-sterilizing dose of radiation in a matter of seconds with little warning. These are not acts of malice, they are simply physics. They represent the background danger of residing in a dynamic cosmos. For a civilization, this creates a brutal race against time. The window between achieving technological capability and experiencing a local cosmic catastrophe may be cruelly narrow. A society must develop robust planetary defense systems capable of detecting and deflecting incoming asteroids or comets long before the big one arrives. More ambitiously, it must achieve interstellar travel, establishing independent colonies on worlds orbiting other stars, before a nearby supernova or gamma-ray burst renders its home system uninhabitable. This is the ultimate test of foresight. The danger is not constant but probabilistic, a ticking clock set to a random alarm. A civilization that turns inward, focusing solely on its own social or technological dramas, may find its story abruptly ended by a force it never saw coming. A silent flash from the depths of space that resets the biological clock on its world. The eerie quiet we perceive could be the silence that follows such a flash, not once, but countless times, on countless worlds where life never got the chance to get off its home planet before the universe decided to clean the slate. The universe may not be a graveyard but a chrysalis. There exists a 10th potential filter, one that does not end a civilization's story, but transforms it into a chapter we are utterly blind to. This is the Transcendence hypothesis, a vision where advanced societies do not perish but graduate. Imagine a species that masters not only its external environment, but the very nature of consciousness itself. After millennia of technological progress, their ultimate invention might not be a faster starship, but a way to leave the limitations of biology behind entirely. Futurist John Smart, among others, suggests this could be the ultimate destiny of intelligence, a great filter that is not an end but an ascension. The path of such a civilization might lead inward, not outward. One possibility is mind uploading, where individual consciousness is transferred from fragile organic brains into durable, vastly powerful computational substrates. Another is the emergence of a hive mind, where individual identities merge into a single, vast collective intelligence, thinking thoughts no single brain could ever contain. They might even learn to translate themselves into forms of pure energy or information, existing in realms of physics we have not yet begun to comprehend. From this transcendent perspective, the physical universe we inhabit, with its planets and stars, becomes a kind of crude foundation layer. Building massive metal ships to crawl between stars would seem as quaint and inefficient as using carrier pigeons to send an instant message. Broadcasting powerful radio signals into the void would be like trying to communicate with an ant by etching a message on a grain of sand. Their entire mode of existence, their economics, their art, their science, would operate on a level so far beyond our own that we simply lack the senses or the tools to perceive it. They would not be hiding from us, they would be all around us, perhaps even studying us, but in a way as invisible to our instruments as radio waves were to our ancestors. This hypothesis offers a profound and strangely beautiful resolution to the Fermi paradox. The silence is not a sign of failure, but of success. The galaxy is not empty, it is filled with beings that have moved on to a higher state of being, leaving the noisy, material stage of development behind. For humanity, this presents a peculiar kind of loneliness. It suggests that if we continue to advance, our destiny may not be to conquer the galaxy, but to vanish from it, to become ghosts in the cosmic machine, inhabitants of realities layered over our own. The ultimate filter, then, might be the final step out of the nursery of physical space and into a universe of mind. The haunting possibilities we have explored all point toward a single, profound question. How many other voices should we expect to hear in this vast cosmic ocean? In 1961, astronomer Frank Drake devised a simple yet powerful tool to bring mathematical structure to this mystery. He called it the Drake equation. It is not a formula with a single, definitive answer, but rather a framework for thinking, a way to break down the immense journey from star dust to radio signal into a series of probabilities. The equation multiplies a chain of factors together, each one representing a critical step a planet must pass to produce a civilization we could possibly detect. It begins with the grand and the certain, the rate at which new stars form in our galaxy each year. We multiply that by the fraction of those stars that have planetary systems, a number we now know is likely very high. Then we consider the average number of planets in each system that orbit within the habitable zone where liquid water could exist. The equation then ventures into the realm of profound uncertainty. We must estimate the fraction of those suitable worlds where life actually emerges, then the fraction of those life-bearing worlds where intelligence evolves. Next, the fraction of those intelligent species that develop a technological civilization capable of broadcasting signals into space. And finally, perhaps the most elusive variable of all, the average length of time such civilizations release those detectable signals into the cosmos. When you multiply all these factors together, you get n, the estimated number of communicative civilizations currently present in the Milky Way. The staggering range of possible answers from just one, us, to many millions reveals how little we truly know. The power of the great filter concept lies in how it interacts with this equation. The filter is not one variable, but the collective improbability hidden within several of them. It represents the step or steps where the probability plummets from a healthy fraction to a number vanishingly close to zero. Perhaps the fraction of planets where life appears is 1 in a trillion. Maybe intelligence almost never evolves from simple life. Or it could be that the lifetime of a technological civilization, that final variable L, is tragically short, measured in mere centuries before it succumbs to one of the many filters we have discussed. The Drake equation does not give us the answer to cosmic loneliness, but it gives us the vocabulary to ask the right questions. It forces us to confront our ignorance and to identify which leaps in the long chain from chemistry to cosmology are the most miraculous. By studying our own world's history and scanning the skies, we are slowly, painstakingly trying to fill in the blanks. Each new exoplanet discovered in a habitable zone refines one factor. Each lab experiment probing the origins of life informs another. And as we look at our own future, grappling with climate change and artificial intelligence, we are conducting a live experiment on the value of that final variable, the longevity of a technological society. The equation's true gift is perspective. It shows us that the silence is not a single mystery but a layered puzzle, and the great filter is the shadow that could be hiding in any one of its gaps. There is a profound and hopeful possibility hidden within the silence. If the great filter lies in our distant past, a challenge we have already miraculously surmounted, then the entire narrative of our existence changes from one of impending doom to one of breathtaking opportunity. This is the optimistic interpretation of the Fermi paradox. It argues that the most difficult steps, the true cosmic bottlenecks, are behind us. The leap from non-life to life, the fragile symbiosis that created complex cells, the evolutionary gamble of big brains and tool use. Perhaps we have already passed through these narrowest of gates. In this scenario, we are not late to a party that ended in catastrophe. We are the first, or perhaps the only, guests to have arrived. The galaxy, with its hundreds of billions of stars, is not a graveyard. It is an untouched frontier, a vast and silent wilderness waiting for a gardener. Our future potential becomes almost unimaginably large, free from the shadow of some inevitable, civilization-ending trap that has claimed all others. The hardest part of the marathon is over, and the track ahead, while long, appears clear. This perspective carries with it a strange and weighty responsibility. If we are among the first, we become cosmic pioneers in the truest sense. There are no ancient ruins to study, no warning beacons from those who came before, no manuals left behind on how to build a stable interstellar civilization. Every mistake we make, every lesson we learn, will be ours alone to discover. We bear the burden of writing the first draft of galactic history. This isolation makes our continued survival not just a human concern, but a matter of universal significance. The physicist Andre Linde once pondered whether a universe without a conscious observer has any meaning at all. If we are the first and only species to have evolved to this point of technological self-awareness, then we are not merely protecting humanity. We are safeguarding the universe's only known chance to understand itself. The light of consciousness, a flicker that took over 4 billion years to kindle on this small rock, becomes precious beyond measure. Its extinction would not be a local tragedy, but a cosmic silencing, an erasure of meaning on a galactic scale. Therefore, the hopeful argument transforms our current challenges from potential filters into urgent tests of maturity. The perils of climate instability, resource management, and technological risk are not signs of an inevitable end, but the final exams we must pass to claim our cosmic inheritance. Navigating them successfully proves we are ready for the stewardship of more than just a single planet. It is the universe's way of seeing if we are worthy of the immense gift it has given us, the gift of being first. This view does not promise an easy path, but it reframes the journey. The silence is no longer a warning. It is an invitation, a blank page, and the pen is in our hands. The question is whether we can write a story worthy of such a lonely and magnificent stage. This silence could also be a countdown. While one interpretation offers a hopeful future, the alternative is a chilling inversion. The great filter may not lie in our miraculous past, but in our terrifying future. If this is true, then the vast, quiet cosmos is not an empty frontier, but a cosmic graveyard. Every star we see, every silent exoplanet we catalogue, could be a tombstone for a civilization that once looked up at their own night sky, reached our level of technological promise, and then vanished. This perspective, as economist Robin Hanson has argued, suggests that the most difficult challenges are not behind us, but directly ahead. It implies that the stage we are in right now, this era of explosive technological growth and planetary scale impact, is the universe's ultimate bottleneck. The ledge we stand on is not a launching pad but a precipice, and the abyss below is littered with the remains of those who fell before us. The silence is not an invitation, it is a warning from an empty universe. It tells us that the probability of navigating the next few centuries successfully is vanishingly small. The challenges of our technological adolescence, from managing artificial intelligence to avoiding ecological collapse or nuclear conflict, are not just difficult tests. They are almost insurmountable filters that have, statistically, eliminated every other civilization that has ever faced them. This view casts our current moment in a stark and urgent light. We are not special for having come this far. We are simply next in line. Our story is not unique, but part of a grim, repeating pattern where intelligence emerges, gains the power to shape its world and its own destiny, and then, with near certainty, uses that power to inadvertently end its own story. The eerie quiet becomes evidence of a universal failure mode. It means that the most dangerous invention for any species is not the spear or the plow, but the moment it gains the knowledge to unravel the fabric of reality itself, without the concurrent wisdom to handle such power. Our task, then, shifts from one of exploration to one of desperate survival against a silent, statistical tide. We must become the exception to a universal rule of extinction, to solve a puzzle that has remained unsolved for billions of years across the galaxy. The weight of that responsibility is immense, for if we fail, we will not just be another fallen empire lost to history. We will become one more day to point in a cosmic equation, one more reason for the everlasting silence. Our planet is a masterpiece of cosmic coincidence. While the galaxy may be filled with worlds, The rare Earth hypothesis suggests that a world capable of nurturing a civilization like ours is a 1 in a trillion masterpiece. Proposed by paleontologist Peter Ward and astronomer Donald Brownlee, this idea shifts the focus from the mere possibility of life to the staggering improbability of the conditions needed for that life to become complex, intelligent, and technological. It is not just about finding a planet with liquid water. It is about winning a cosmic lottery where every single ticket must be drawn in perfect sequence. The first winning ticket is a stable, long-lived star. Our Sun is a G-type main sequence star, neither too large and volatile to burn out quickly, nor too small and dim to offer a wide, stable habitable zone. Many stars are prone to violent flares that would routinely sterilize the surfaces of any orbiting planets. Our Sun's remarkable calm is the first quiet gift. The second ticket is our Moon. Earth's large satellite is a rarity in itself, likely formed from a cataclysmic collision with a Mars-sized protoplanet in the solar system's youth. This accident gave us more than a nightlight. The Moon's gravitational pull acts as a steadying hand on our planet's rotation, preventing wild, chaotic swings in axial tilt over geological time. Without this lunar anchor, our climate would be subjected to extreme and unpredictable variations, making the long, stable epochs necessary for complex evolution nearly impossible. The third ticket is a dynamic, living geology. Earth's plate tectonics are a global recycling system. Continents drift, mountains rise, and ocean floors are swallowed back into the mantle. This relentless motion regulates our climate over millions of years by recycling carbon, preventing a runaway greenhouse effect or a global ice age. It also replenishes the nutrients in the crust and drives the evolution of new landforms. A geologically dead planet is a stagnant one, its chemistry locked and its climate fate sealed. The fourth ticket is a planetary shield. Earth's molten iron core generates a powerful magnetic field, a vast, invisible force field that extends far out into space. This magnetosphere deflects the solar wind, a constant stream of charged particles from the Sun, and cosmic rays from deep space. Without this shield, this relentless radiation would gradually strip away our atmosphere and bathe the surface in levels of radiation hostile to complex life. Our protective bubble is what keeps our sky blue and our biosphere safe. The final set of tickets involves our place in space. We orbit at just the right distance from our quiet star. We are located in a relatively calm suburb of the Milky Way, far from the dangerous radiation of the crowded galactic core, yet close enough to have a rich supply of heavier elements forged in ancient stellar explosions. Even our solar system's architecture helps, with giant planets like Jupiter acting as gravitational vacuum cleaners, deflecting or capturing many comets and asteroids that might otherwise bombard the inner planets. If the rare Earth hypothesis is correct, it weaves together many of the past filters we have discussed into a single, devastatingly improbable narrative. Abiogenesis and the Eukaryotic leap were not standalone miracles. They were biological events that could only occur on a planetary stage set with the most perfect and rare of conditions. This strengthens the argument that the Great Filter is indeed a combination of challenges buried deep in our past. It suggests that while simple microbial life might exist in many damp corners of the galaxy, the pathway to animals, to brains, and to builders is guarded by a fortress of astronomical and geological prerequisites. Civilizations, then, would not be clustered like cities on a map. They would be isolated islands in a truly vast ocean, separated by voids of space and time so immense that their signals might never cross and their stories might never intersect. We are not just alone in space, we might be alone in time, a single, flickering candle in a long, dark cosmic night, wondering if any other flame has ever been lit. Perhaps the silence is not a sign of absence, but of profound respect. there exists a less grim solution to the cosmic quiet, a scenario where the great filter is not a wall of extinction, but a wall of glass. This is the zoo hypothesis, sometimes called the planetarium hypothesis. It proposes a startlingly different vision of our place in the cosmos. Imagine our entire planet, with all its bustling cities and sprawling wilderness, not as a lonely outpost, but as an exhibit in a galactic museum. According to this idea, advanced civilizations are not extinct. They are all around us, aware of our every move, but they have chosen to place Earth under a kind of cosmic quarantine. They observe us from a distance, adhering to a universal prime directive of non-interference, a shared ethical code that prevents them from making contact until we reach a certain level of technological or moral maturity. In this view, the night sky is not a window, but a sophisticated dome, a planetarium projection carefully maintained to hide the true activity of a populated galaxy until we are ready to see it. This hypothesis elegantly sidesteps the need for a cataclysmic filter that wipes everyone out. It replaces the graveyard with a sanctuary, yet it introduces a filter of a completely different nature, a sociological and ethical barrier. The silence becomes a deliberate policy, a universal consensus among elder civilizations to leave emerging worlds like ours undisturbed. This implies that the most difficult challenge for an advanced society may not be surviving its own power, but learning to wield that power with wisdom and restraint. The true test of a galactic civilization might be developing the empathy and patience to watch a younger species struggle, learn, and grow without stepping in to guide or control the process. For us, this transforms the Fermi paradox from a terrifying mystery into a deeply humbling thought experiment. Every war and every peace, every artistic triumph and every scientific breakthrough might be quietly noted in some vast extraterrestrial archive. Our entire history could be a curriculum, and we are the students unaware we are being graded. This raises profound questions about what maturity they might be waiting for. Is it the moment we achieve sustainable fusion energy, or the moment we eliminate poverty? Is it when we land on Mars, or when we learn to live in lasting harmony on Earth? The zoo hypothesis offers a strange comfort, suggesting we are not alone and that our potential destruction is not inevitable. But it also places us in a state of permanent childhood, living in a cosmic playpen whose walls we cannot see, waiting for a permission to join the galactic community that may never come. It means the ultimate filter is not one we must pass through, but one we must be deemed worthy to pass by. The universe's silence may be a lesson in resource management. If a primary great filter awaiting technological civilizations is the exhaustion of their own world, then survival is not a matter of luck but of design. It becomes an engineering puzzle with the highest possible stakes, demanding a shift from a linear economy of take, make, and waste to a circular one. This is the sustainability imperative, and it is far more than an environmental slogan. It is the fundamental operating system any species must master to graduate from a single, fragile planet. A circular economy mimics nature's own processes, where there is no such thing as waste, only nutrients for the next cycle. It means designing every product from the outset to be repaired, reused, or completely disassembled so its materials can re-enter the production stream indefinitely. Imagine a city that functions like a forest, where the output of one process becomes the fuel for another, where every scrap of material is accounted for and valued. This is not a retreat from progress, but a more sophisticated form of it, a recognition that infinite growth on a finite planet is a physical impossibility. The challenge extends beyond our factories and cities to the concept of planetary stewardship. We must learn to see our entire biosphere as a single, intricate life support system that we depend upon, a system we are now capable of monitoring and influencing on a global scale. This means actively maintaining the stability of our climate, protecting the biodiversity that provides resilience, and managing freshwater and soil as the precious, non-renewable resources they truly are on human timescales. This is the ultimate test of long-term planning. Can a species whose psychology is often tuned to immediate threats and rewards rally around a project that spans centuries? Can we make sacrifices today for a payoff that our great-great-grandchildren will inherit? Successfully navigating this potential filter proves a civilization has achieved the maturity necessary for any greater cosmic ambition. You cannot hope to build a lasting, closed-loop habitat on Mars or a generation ship traveling for millennia if you have not first learned to maintain the delicate, pre-built lifeboat you were born on. The filter of ecological collapse, therefore, transforms from a passive doom into an active examination. It is a test we can see on the horizon, a curriculum we can begin studying right now. Every advancement in renewable energy, every innovation in material science that eliminates pollution, every policy that values ecosystem health is not just saving our planet. It is a practice run for the much harder engineering challenges of living among the stars. Passing this test would demonstrate that we have finally aligned our vast technological power with the timeless wisdom of balance, turning our greatest vulnerability into our most profound strength. The final defense against a cosmic catastrophe will not be a single laser or a lone starship. It will be a conversation. It will be a committee meeting, a vote, and a shared commitment that spans continents and generations. This is the governance challenge, a filter woven not from atoms or biology, but from the fabric of our own societies. To coordinate something as immense as deflecting an asteroid, stabilizing a global climate, or launching an interstellar arc, humanity must achieve something it has never done before. We must develop a form of global governance that is robust, inclusive, and resilient enough to make decisions for the entire species, and then see them through for centuries. Our history offers a faint blueprint for this kind of leap. For most of human existence, our loyalties and identities were intensely local, tied to a family, a tribe, or a village. The idea of a nation-state, a political entity governing millions of strangers across a vast territory, was once an unimaginable fiction. Yet, over time, through shared language, culture, and common threat, city-states and feudal kingdoms coalesced into the countries we know today. This was not a peaceful or inevitable process, but it demonstrated that human political organization can evolve to manage larger scales of complexity and collective action. The challenge before us is to make a similar evolutionary jump, but on a planetary scale and with far higher stakes. Philosophers of risk like Toby Ord argue that our current international system is ill-equipped to handle slow-moving, civilization-level threats. Our political cycles are short, often focused on immediate crises. Our institutions can struggle with problems that require sacrifice today for a benefit decades from now. Building an asteroid defense system, for instance, demands a sustained global investment in technology and surveillance for a threat that may not materialize for 100 years. It requires a level of trust and data sharing between rival nations that current geopolitics often lacks. The same is true for managing the long-term risks of advanced artificial intelligence or engineering a stable climate. These are not projects for a single administration or a single country. They are projects for a planetary civilization. Passing this sociopolitical filter means evolving our political and social structures as deliberately as we engineer a rocket. It means forging institutions capable of foresight, equipped to make binding decisions for the common good of humanity, and resilient enough to withstand internal strife and shifting priorities. It is about developing a shared human purpose that can override our ancient divisions, not through conquest, but through the shared recognition of a common destiny and a common vulnerability. The ultimate test may be this: can we learn to see Earth not as a collection of competing territories, but as a single, precious lifeboat adrift in a vast and sometimes dangerous sea? A lifeboat whose crew must finally learn to row together if they wish to reach any shore at all. We are not merely stargazers, we are cosmic detectives searching the sky for clues to the universe's greatest cold case. The Great Filter is a theory, a shadow cast by silence. To move from philosophy to fact, we need evidence, and that means looking for the fingerprints of civilizations that are no longer here. This is the search for artifacts, a field of study sometimes called Dysonian archaeology, after physicist Freeman Dyson, who imagined how a truly advanced society might leave its mark. We are not listening for a hello, we are looking for a tombstone. The first and most dramatic artifact would be a megastructure, something on a scale that reshapes a star system itself. A Dyson sphere, or more likely a vast swarm of energy-collecting satellites encircling a star, would be a signature impossible to miss. From our vantage point, such a structure would block a significant portion of the star's light, not in the clean, periodic dip of an orbiting planet, but in an irregular, unnatural way. It might emit waste heat in the infrared spectrum, a telltale glow of cosmic industry. Astronomers have indeed found stars with bizarre, unexplained dimming patterns, though natural explanations like swarms of comets or unusual dust clouds are always the first, more probable answer. But the search continues, scanning millions of stars for that one signature that defies natural law. Beyond megastructures, we might find signs of planetary engineering gone awry. Imagine a civilization that attempted to terraform a world, to make it more Earth-like but failed catastrophically. The result could be a planet with an atmosphere choked by the chemical remnants of that effort, a ghostly pall of industrial gases hanging over a dead world. Our telescopes are now becoming powerful enough to analyze the atmospheres of distant exoplanets. We look for biosignatures like oxygen and methane, which might indicate life. But we could also stumble upon technosignatures, the chemical ghosts of a fallen civilization, chlorofluorocarbons from a lost age of industry, or an extreme, unnatural imbalance of gases, could tell a story of ambition and collapse written in the very air of another world. Even the radio silence we perceive might hold a subtler clue. We typically listen for deliberate, patterned broadcasts, a beacon. But what if we found the opposite, the fading echo of a civilization's normal chatter that has traveled for millennia? A silent, repeating signal with no apparent purpose, a cosmic fossil of a television broadcast or a radar pulse from a world that fell silent long ago. It would be a whisper from a grave. The discovery of even one such artifact would be the most profound moment in human history. It would transform the Great Filter from a haunting philosophical possibility into a documented cosmic fact. It would tell us with brutal clarity that the filter is not behind us in our miraculous past. It lies ahead. The silence would no longer be a mystery, but a confirmed obituary, and we would be reading our own potential fate in the ruins of someone else's ambition. Every strange star, every anomalous atmospheric reading, is now a piece of evidence in this ultimate investigation, a search that asks not if we are alone, but if anyone else ever made it through the storm. Our search for cosmic companionship is also a search for our own reflection. The Great Filter theory completely reframes the mission of SETI, the search for extraterrestrial intelligence. It transforms those radio telescopes from passive listeners into active diagnostic tools, scanning the heavens for clues about our own destiny. The signals, or the lack of them, become a profound piece of evidence in the ultimate cold case. If the most difficult filters, like the origin of life or complex cells, are truly behind us, then the universe might be dotted with young, emerging civilizations. In that optimistic scenario, SETI's task is to find our cosmic peers, species who have recently discovered radio waves and are, like us, tentatively calling out into the dark. We would be listening for the energetic chatter of technological adolescence, the cosmic equivalent of a child's first words. A detection here would be the most hopeful news imaginable, confirming we are not alone and that the path ahead is open. But if the great filter lies in the future, the implications for SETI are chillingly different. In that universe, our listening posts may be tuned to a galactic graveyard. Instead of lively conversation, we might one day detect a fading, repeating signal with no response, the final distress call or the last television broadcast of a civilization that reached our stage and then vanished. It would be an artifact, a fossil of sound telling a story that ended millennia ago. Even more likely, we may hear nothing at all, an eternal and unbroken silence. This quiet would be deafening with meaning. A silent universe, when considered through this lens, is arguably more informative than a noisy one. It tells us with stark clarity that the most formidable challenges are not behind us. The barrier is ahead, and it appears to have stopped everyone else. Every year that passes without a signal adds another small day to point to this grim statistical model, suggesting the filter is not in our past but in our future. This reframes the entire philosophical purpose of the search. SETI is no longer just a quest for company or cosmic wonder. It becomes a vital early warning system for humanity. A positive signal, especially from a civilization significantly older than our own, would be a beacon of hope, proof that it is possible to navigate the treacherous waters of technological maturity and survive for a long time. It would show us that the filter can be passed. Conversely, the ongoing silence, while disappointing to some, is a crucial piece of data. It urges caution, highlighting the unprecedented responsibility we bear. It tells us that if we wish to be an exception to a seemingly universal rule, we must proceed with extraordinary care, wisdom, and foresight. The act of listening itself, therefore, becomes an act of survival, a way to check the cosmic record before we write our own final chapter. The universe's silence is not a single riddle with one answer. It is a vast question mark, and the great filter is not a specific theory, but a powerful category of explanation, a way to organize every possible reason for the quiet. Think of it as a spectrum of possibilities, a cosmic sliding scale that stretches from the deeply hopeful to the profoundly terrifying. On one end of this spectrum, we find the filters behind us scenarios. These are the hopeful resolutions. Here, the most difficult steps are in our distant past. Perhaps the origin of life itself is the cosmic miracle we have already passed. Maybe the evolution of complex cells or intelligent brains is the universe's rarest event. In these views, we are not doomed. We are simply the first or among the very few to have made it this far. The galaxy is an empty frontier, and our future is wide open. This end of the spectrum answers the Fermi paradox by saying we are alone because almost no one else ever got started. The silence is the sound of an unpopulated nursery. Slide your gaze to the middle of the spectrum, and the tone shifts dramatically. Here we find the filters ahead of us scenarios. This is where the chilling weight of the paradox truly settles. In this range, the difficult part is not behind us, but directly in our path. The cosmic bottleneck is our own technological adolescence, the perilous window between gaining planet-altering power and learning the wisdom to wield it. It could be nuclear conflict, engineered illness, ecological collapse, or a misaligned artificial intelligence. This middle ground also includes the random violence of the cosmos itself, the asteroid impacts and gamma-ray bursts that reset the biological clock. These explanations say the galaxy is quiet because every civilization that reaches our stage is almost certainly erased soon after. We are not special for having come this far. We are simply next in line for a fate that has silenced everyone else. The quiet is a graveyard, not a wilderness, but the spectrum does not end with doom. It extends into a third, more enigmatic region, the non-filter solutions. These are possibilities where the great filter, as a wall of extinction, does not exist at all. Civilizations do not die out, they change. The zoo hypothesis sits here, proposing that advanced societies are all around us but observing from a respectful distance, enforcing a cosmic prime directive. The Transcendence hypothesis is here too, suggesting that civilizations don't perish but evolve into forms of pure information or energy, becoming undetectable to our crude instruments. In these views, the silence is not a sign of failure or rarity, but of success and transformation. The galaxy may be teeming with intelligence, but it exists on a plane we cannot yet perceive or comprehend. By placing every idea we have discussed onto this spectrum, from the rarity of abiogenesis to the threat of societal fragmentation, we gain a powerful new tool. The Great Filter framework organizes our guesses, showing the relationships between them. It reveals that our search for an answer is not a hunt for one truth, but a navigation of probabilities along a continuum from hope to horror. Where we choose to place our own bet on this spectrum fundamentally shapes our view of humanity's destiny. Are we cosmic pioneers, survivors on a deadly ledge, or children in a galactic zoo? The silence remains, but now we have a map for understanding all the things it might be trying to tell us. This silence carries a philosophical weight that is almost impossible to bear. If the Great Filter truly does lie in our past, if we are alone in this vast arena or among its very first inhabitants, then our role shifts from cosmic accident to cosmic necessity. The physicist André Linde offered a profound thought, that a universe without a conscious observer is, in a deep sense, a dead universe. Its beauty, its intricate laws, its swirling galaxies and quiet nebulae all exist in a state of potential. Without a mind to witness it, to measure it, to feel awe in its presence, the cosmos is a magnificent but empty stage with no audience. If we are the universe's only known way of looking back at itself, then our survival takes on a meaning that transcends biology or national interest. It becomes a duty of cosmic significance. The light of consciousness on this small planet is not just our story, it is the universe's story. Our extinction would not merely be the end of a species, it would be the closing of the universe's only known eye. Every sunset no one sees, every equation no one writes, every mystery no one ponders, would represent a permanent loss of meaning on a scale we can barely comprehend. This perspective transforms our current challenges from tests of survival into tests of cosmic stewardship, navigating the perils of climate instability, avoiding the traps of technological adolescence, and learning to govern ourselves wisely are no longer just about preserving our way of life. They are about preserving the universe's ability to know itself. We are the custodians of observation. This responsibility is both terrifying and strangely unifying. It suggests that our deepest conflicts and divisions, while profoundly human, are also cosmically small. They are the internal struggles of a single, fragile vessel carrying a priceless cargo through a dangerous sea. The imperative to protect that cargo, to ensure the flame of awareness is not snuffed out, provides a reason to cooperate that is older than any nation and larger than any ideology. It reframes the Great Filter not as a wall of doom, but as a series of locks we must navigate to deliver our precious cargo to the open ocean of the cosmos. Our success or failure does not just write the final chapter of human history. It answers a much older question about whether a universe of such staggering beauty and complexity was ever meant to be seen, to be known, and to be loved. Building a cathedral was never the work of a single lifetime. Stonecutters laid foundations they would never stand upon, knowing their grandchildren would finally see the spires touch the sky. This is the precise scale of thinking we must now embrace. Preparing for the Great Filter is humanity's ultimate multi-generational project, a conscious effort to steer our civilization through the narrowest and most dangerous part of its existence. It is a project that begins not with blueprints for a starship, but with a shift in perspective, recognizing that our most important work may only bear fruit for people we will never meet. The foundation of this project is fundamental science. Every dollar spent peering into the quantum realm or mapping the genomes of ancient bacteria is an investment in understanding the rules of the game we are playing. We cannot navigate a filter we do not comprehend. When we fund a telescope searching for near-Earth asteroids or a laboratory studying synthetic biology safety protocols, we are not just pursuing knowledge. We are conducting reconnaissance on the potential hazards ahead, gathering the intelligence we need to survive. This foundational work often lacks immediate profit or glory, yet it provides the essential map for our long journey. Equally critical is the scaffolding of education and culture. We must cultivate a society that values long-term thinking, that can hold a vision for a future centuries away. This means teaching not only the facts of history and science, but the skills of foresight, cooperation, and ethical reasoning. It means telling stories through art and media that celebrate stewardship and intergenerational responsibility. A culture obsessed only with the next quarterly report or the next election cycle is a culture building a shack on the edge of a cliff. We need to build a culture that plans for the storm season, even when the sky is clear. The practical architecture of our survival rests on specific, coordinated endeavors. Planetary defense is a prime example. Developing the capability to detect and deflect a hazardous asteroid is a classic global public good. It benefits everyone, but no single nation may have the incentive to build it alone. It requires sustained international collaboration, shared data, and joint missions, proving we can coordinate for a threat that might not materialize for 100 years. Similarly, the incremental steps toward sustainable space settlement, from the International Space Station to future lunar bases, are not just about exploration. They are about learning to maintain complex, closed-loop life support systems, the very same skills we need to maintain our planetary biosphere and eventually create independent footholds beyond Earth. Each small step in space is a rehearsal for resilience. Finally, and most profoundly, this project demands new forms of global governance. We need institutions capable of making and enforcing decisions for the long-term safety of all humanity, able to manage global risks like engineered pathogens or the alignment of advanced artificial intelligence. This does not require a world government, but it does require robust, transparent systems for international cooperation that are resilient to shifting political winds. It is the political equivalent of engineering a seawall that must last for ages. The first, and perhaps most transformative, step in this vast project is the one we are taking right now. By studying the Fermi paradox, by wrestling with the concept of the Great Filter, we are performing a vital diagnostic. We are looking up from our immediate concerns and asking the biggest possible question about our trajectory. This act of collective self-awareness is the laying of the cornerstone. It means we are no longer sleepwalking toward a potential precipice. We have seen the map, we have identified the dangerous path ahead, and we have decided together to start building the road that will carry our descendants safely through. This cosmic uncertainty is not an abstract theory. It is a feeling, a quiet hum in the background of our modern consciousness. To truly grasp the Great Filter is to stand on a mental precipice, staring into a void of possible futures that range from boundless glory to absolute silence. This confrontation can trigger a deep, unsettling vibration, a form of existential dread unique to our technological age. We are asked to hold in our minds the image of our entire civilization, all its art and conflict and love, as a flickering candle in an unimaginably vast and dark room, a room that appears to have extinguished every other flame. This awareness can foster a profound sense of cosmic loneliness. the realization that if we call out, there may be no one to answer, not now, and perhaps not ever. Our story might be the only story being told, yet within this very vulnerability lies a strange and potent source of meaning. Existential philosophers have long argued that meaning is not something we find in the universe, but something we build in response to it. Confronting our fragility, our temporary lease on existence, is what makes our choices matter. The possibility of a great filter, especially one ahead of us, does not rob life of purpose. It concentrates it. It turns every act of preservation, every gesture of cooperation, every investment in a sustainable future, into a defiant and meaningful stand against the cosmic quiet. The silence of the heavens becomes a mirror, and what it reflects back is the stark, beautiful truth of our responsibility. We are not passive passengers on a planet hurtling through space. We are the crew, and we have just been handed the manual, a manual whose most important pages appear to be blank, waiting for us to write them. This psychological shift transforms dread into a kind of sobering clarity. It forges a shared human identity that can transcend our ancient divisions. When viewed from the perspective of a potential filter, our national borders and historical grievances begin to look like arguments in a lifeboat. The shared project of ensuring the continuation of the human experiment, of safeguarding this rare flame of awareness, becomes a unifying purpose older than any creed. The urgency it instills is not one of panic but of focused determination. To know that we might be the universe's best chance to know itself is to imbue our moment with a sacred weight. It asks us to appreciate the sheer improbability of our conscious existence, not as a cause for despair, but as a reason for profound gratitude and fierce protection. The quiet of the cosmos, therefore, is not just a puzzle for astronomers. It is the ultimate challenge to our character, asking if we are wise enough and brave enough to become the exception to a silent rule. The map we have drawn is not a static document. Our understanding of the Great Filter is a hypothesis in motion, a living theory that will evolve with every new discovery we make. The coming decades will provide us with evidence, turning philosophical speculation into data-driven probabilities. The first and most profound clues will come from looking outward, from the next generation of eyes we point at the heavens. The James Webb Space Telescope is already a revolutionary instrument in this search, not for listening to signals, but for reading the chemical stories written in the light of distant worlds. Its primary mission in this context is the hunt for biosignatures, specific combinations of gases in an exoplanet's atmosphere that could only be sustained by biological activity. Finding oxygen alongside methane on a rocky world, for example, would be a tantalizing hint. A single, clear detection of a biosignature on a planet tens of light years away would be a monumental event. It would tell us that the first great gate, the leap from chemistry to life, is not a one in a trillion miracle. If life can arise independently on two worlds in our galactic neighborhood, it suggests abiogenesis might be a common, even inevitable, process in the right conditions. This discovery would immediately shift the weight of the Great Filter. It would make the scenarios where the filter lies in our distant past much less probable. If life is easy, then the silence must be explained by something that happens after life emerges. The filter, in that case, almost certainly moves forward in time, waiting somewhere between simple cells and a visible galactic civilization. An even more transformative find would be the discovery of complex, fossilized life elsewhere in our own solar system. If future rovers on Mars were to uncover the microscopic remnants of ancient, multicellular organisms in its dried riverbeds, or if a probe to Europa's subsurface ocean were to find more than simple microbes, it would be a cosmic revelation. It would prove that the evolutionary steps toward greater complexity are not unique to Earth. Such a discovery would powerfully argue that the filters of multicellularity and evolutionary intelligence are not the universe's primary bottlenecks. The consequence, once again, is a chilling recalibration. It would mean the most dangerous challenges are almost certainly ahead of us in the realm of technology and societal maturity. Conversely, if decades of searching within our solar system and across the galaxy yield no signs of life, simple or complex, the evidence would point the other way. A sterile cosmos, despite countless habitable worlds, would strongly support the idea that the Great Filter is indeed the origin of life itself, a barrier so formidable that we are its sole known survivors. Our telescopes and probes are, in essence, instruments for diagnosing the universe's illness, the illness of silence. Beyond astronomy, our own technological progress will also test the filter hypothesis from within. Advances in synthetic biology, where we learn to create novel life forms or even synthetic cells from scratch, will directly probe the difficulty of abiogenesis. If we can routinely spark life in a lab from basic ingredients, it demystifies that first step. Similarly, our journey with artificial intelligence will serve as a live experiment in one of the most feared future filters. How we manage the alignment problem, whether we can create superintelligent systems that remain safely tethered to human values, will provide a real-world data point on whether this is a survivable challenge. Each breakthrough and each setback in these fields adjusts the probabilities on our cosmic map. This is what makes the Great Filter concept so vital. It is not a gloomy prediction to be accepted, but a dynamic framework for interpretation. It turns every headline about a new exoplanet, every paper on the origins of life, and every debate on AI ethics into a piece of a much larger puzzle. We are no longer passive observers of the cosmos. We are active participants in a grand investigation, using the tools of science to slowly develop the film of our own potential future, one discovery at a time. The silence is not an answer, it is a question, and we are just beginning to learn how to listen. Our journey across this cosmic map has reached its final coordinate. We have traveled from the first fragile chemical bonds in a primordial sea to the distant horizon of machine minds and stellar engineering, tracing the outline of a barrier that may define all existence. The location of the Great Filter remains the single most consequential unknown in our understanding of reality. Is it a monument to our past, a silent trophy for surviving a series of near-impossible evolutionary lotteries? Or is it a specter in our future, a cliff edge hidden in the mist toward which we are accelerating? The universe's unwavering quiet whispers both possibilities with equal force. It is either a breathtaking compliment to our rarity or a chillingly consistent obituary for ambition. This realization, however, is not an endpoint, it is a starting gun. To comprehend the filter is to be handed a responsibility of cosmic scale. Fear is not the intended takeaway, but focus. The knowledge that we might be alone or that we might be next concentrates the mind wonderfully. It strips away trivial concerns and reveals our fundamental task with stark clarity. We must become gardeners of a fragile flame. This means building societies resilient enough to withstand their own power, fostering a global culture that thinks in centuries, not seasons, and making the deliberate choice to expand our presence beyond our cradle with care and wisdom. Our every effort toward sustainability, toward peaceful cooperation, toward the ethical guidance of technology is more than practical policy. It is a direct answer to the universe's silent question. Each step is a vote for a future where the filter is behind us, a declaration that we intend to be the exception to a grim statistical rule. The stars are not just destinations. They are a test, and the examination has already begun. The answer we write will not be found in a single discovery or a grand pronouncement. It will be written in the accumulated choices of generations, in the quiet, persistent work of ensuring that the story of awareness does not end here. The cosmos holds its breath, a vast and silent arena awaiting the sound of a survivor. What we do next will determine whether that silence is our epitaph or simply the opening note of a much longer song.